All right, welcome. Today we are cracking the code on one of chemistry's absolute biggest ideas, electron configurations. So how does an atom with, dozens of electrons flying around keep them all in order instead of just descending into total chaos? The answer to that question dictates pretty much everything, from the color of fireworks to the shape of molecules in your own body. So let's dive in. We can understand this whole thing with a simple and honestly pretty clever analogy. I want you to imagine the atom as a high-rise apartment building. It's designed specifically for electrons. The nucleus is like the foundation, and everything else is just built up from there, floor by floor. So the building's floors, those are what we call the main energy levels. We number them 1, 2, 3, and so on, starting right from the ground floor. And it's pretty intuitive. The farther a floor is from the ground, our nucleus, the more energy an electron needs to have to live there. Simple enough, right? Okay, so on each of these floors, you find different types of apartments. Chemists call these sublevels. They go by the letters S, P, D, and F. And each one has a really distinct shape and a different layout, kind of like the difference between a studio and, say, a 3-bedroom apartment. Now, inside each of those apartments are the rooms, or what we call orbitals. Now, an orbital isn't just one spot. It's more like a region of probability. It's the space where an electron tenant is most likely to be found just hanging out. And there is a very strict occupancy limit. Each room can hold a maximum of 2 electrons, no more. And you can see right here how these apartment types get more and more complex. An S apartment is the simplest one you can get. It's just a single spherical room that can hold 2 electrons. A P apartment is bigger, with 3 dumbbell-shaped rooms, so it can hold up to 6 electrons. And from there, the D and F apartments get way larger and more intricate, holding 10 and then 14 electrons. Okay, so how do we pinpoint an electron's exact location in this massive building? Well, we use a set of 4 quantum numbers. You should just think of these as a unique mailing address for every single electron tenant. And here's the key. No 2 electrons can have the exact same address. First up, we have N, the principal quantum number. This one's the easy one. It's just the floor number. Is it on floor 1, floor 2, floor 3? It tells us the main energy level of the electron. Next, we've got L, the azimuthal quantum number. This one tells you the type of apartment on that floor. Is it the simple S apartment or the P, D, or F? This number defines the shape of the orbital. Then there's ML, the magnetic quantum number. This one points to the exact room within that apartment. So for a P apartment, which we know has 3 rooms, those rooms get numbered -1, 0, and 1. This just describes how they're oriented in 3D space. And finally, we have MS, the spin quantum number. This is kind of like the electron's personal ID. It can either be spin up or spin down. And this is so important because it's the key to our first major rule of tenancy. See, electrons don't just move in wherever they feel like it. This is not some chaotic free-for-all. There are 3 very strict tenancy laws they have to follow, and these laws dictate exactly how the building gets filled up. First, there's the Aufbau principle. The easiest way to think about this is the lowest rent first rule. Electrons are, well, they're frugal. They always fill the lowest energy orbitals available before they even think about moving to the more expensive, higher energy floors. So, this leads to a classic point of confusion for a lot of people. You might be asking, wait a minute, if the 3rd floor is lower than the 4th, why do electrons sometimes move into a 4S apartment on the 4th floor before they fill up a 3D apartment back on the 3rd? It seems backwards. Well, the answer is something called the N plus L rule. See, the actual energy isn't just about the floor number. You have to add the floor, N, and the apartment type, L, together. So for a 4S apartment, that's 4 plus 0, which equals 4. For a 3D apartment, it's 3 plus 2, which equals 5. And since 4 is less than 5, the 4S apartment is actually cheaper. It has lower energy, so it gets filled first. Okay, next up, the Pauli exclusion principle. This is the absolute, ultimate, no duplicates rule. What it says, officially, is that no 2 electrons in an atom can have the exact same set of 4 quantum numbers. They simply cannot have the same address. And this shows you exactly what I mean. Let's say 2 electrons share the same room. That means they have the same floor, the same apartment, and the same room number. Well, because of the rule, their final quantum number, their spin, has to be opposite. One is spin up, the other is spin down. They can be roommates, for sure, but they can never be identical twins.
And finally, there's Hund's rule, which I personally like to call the roommate rule. Basically, when electrons move into an apartment that has multiple empty rooms of the same energy, like a p or a d sublevel, they prefer their personal space. Each electron will grab its own empty room before they're ever forced to pair up and share.
So there you have it. Those are the rules. Fill from low to high, no duplicates, and spread out before you pair up. But in the totally weird world of quantum mechanics, some elements have figured out how to cleverly bend those rules. Take a look at chromium. Now, based on the rules we just went through, you'd totally expect its 4s apartment to be full with 2 electrons and the 3d apartment to have 4. But that's not what happens. What we actually see is that one electron packs its bags, moves out of the 4s, and takes a room in the 3d apartment. This leaves every single one of the 5 3d rooms with one occupant. And then we see the exact same strange thing with copper. The rulebook says it should have a full 4s apartment and a 3d apartment with 9 electrons, just one short of being full. But again, nope, an electron gets promoted, leaving the 4s half empty just so it can completely fill up that last room in the 3d apartment. So what on earth is going on? This seems to break the most basic rule about filling the lowest energy levels first. Well, this isn't some random rebellion. This is a very calculated move. These electrons are exploiting a loophole in the energy system, and they're doing it in the ultimate pursuit of just one thing: stability. So here's the crucial loophole. It turns out there's a special lower energy state, a big stability bonus, that an atom gets when its d sublevel is exactly half full or completely full. The tiny bit of energy it costs to promote one little electron from the 4s is absolutely nothing compared to the massive stability payoff the entire atom gets in return. It's a fantastic deal for the atom. And this stability trick also explains another big puzzle. Why do transition metals lose their 4s electrons before their 3d electrons when they form ions? I mean, it seems totally backwards, right? But once the electrons are actually in the building, all their repulsions start shifting the energy levels around. And that 4s apartment, which was cheaper to move into at first, actually becomes the true outermost highest energy level. It becomes the new valence shell, so its tenants are the first ones to get kicked out. From the way atoms bond together to make molecules, to the brilliant colors of fireworks, these electron configurations are, quite literally, the architectural blueprint for matter itself. I think the big thing to take away here is that the universe is built on this really elegant set of rules. But the most interesting stuff, the most interesting chemistry, often happens when those rules get bent in the search for just a little more stability. Thanks for joining this explainer.